Alright, welcome to part B. Let's get on with it. Question 16 is an experiment question, first-hand investigation on projectile motion. A ball resting on a horizontal table is given an initial push at x, resulting in the ball following the path x, y, z. A data logger used the motion sensor to determine the horizontal distance to the ball. When the ball was at position y, a distance of 1.5 meters from the motion sensor, it left the edge of the table. On the first trial, the range was 60 meters. The graph below was obtained from the data. So we have distance and we have time, so meaning the gradient of this line is going to be velocity because meters per second. For this trial, determine the horizontal speed of the ball as it left the edge of the table. So what I just said here, that the gradient of this line is going to be speed. So all that we have to do is just calculate the gradient, and there we go. This experiment was repeated with the ball leaving the table at different speeds. Graph the relationship between the range and the horizontal speed at y. Identify your graph the results from the first trial. So obviously the more horizontal speed we give it, the further it's going to land the range at right here. If we give it enough velocity, this range is going to get bigger and bigger and bigger. So what we should be seeing is a linear relationship between horizontal speed and range. Okay, and we could probably put in a point there for the first trial. Okay, the apparatus described in this first-hand investigation was used to carry out an identical experiment on another planet, where the acceleration due to gravity was less than that on Earth. The horizontal speed of the ball as it left the table on the planet was the same in part A. Compare the range on that planet to that of Earth. So if the acceleration due to gravity is less, that means it would take more time for it to hit the ground. So if it actually it would take more time. So its range would be greater because during that time horizontal motion stays constant. So the main here is explain. So we need to relate acceleration to the range. So we say the range affects the time it takes to hit the ground, and since the time is increased, it will have more time to travel in the x direction, and thus the range would increase. So remember, explain. And it's 2 marks, so we should be linking together 2 ideas. A satellite of mass 150 kilos is launched from the surface of the Earth into uniform circular motion. Calculate the magnitude of the gravitational potential energy. So magnitude, so they don't care if it's plus or minus, they only care about the size. So potential energy is minus g m1 m2 over r. Just plug that in and we'll get it. Now from this uniform circular orbit, the satellite can escape the Earth's gravitational field when its kinetic energy is equal to the magnitude of the gravitational potential energy. Use this relationship to calculate the velocity of the satellite. Okay. Use to calculate the velocity of the satellite. I'm assuming escape velocity. Anyway, so what we have to do here is equate kinetic energy and gravitational energy, make V the subject, and we can plug in values for V and we'll get it. Discuss the effects of Earth's rotational motion on the launch of the satellite. So compared or relative to the Sun, the Earth's rotational, just relative to whatever, Earth's rotational motion matters a lot. And we really want to be launching in the same direction because its rotational motion adds to our the motion that we set it at, the satellite at, if that makes sense. So it's a discuss, but in this case it's a small verb. It's only two. So discuss. The second meaning of discuss was pretty close to identify and describe. Okay, question 18. Mixon and Morley set up an experiment to measure the velocity of Earth relative to the ether. Outline two features of the ether model. Yeah, this is just a memory question. Outline. So one is that it's like invisible or highly transparent, and another one was high viscosity, and it was also very springy because light had huge frequencies, had really big frequencies, so it had to vibrate as well. So basically, the main feature of the ether model is that it was a medium for light to travel or to transmit light. Recount the Mixon and Morley experiment. So straight away I would write down what was the aim of the Mixon and Morley experiment. There's definitely one mark there, which attempted to measure the relative Earth for the ether. Yeah, that's pretty much it. So we could put in the equipment setup, the hypothesis, so like what they expected to get, and then what they actually got, and describe the results they anticipated. So they anticipated to measure an interference pattern and use that interference pattern to calculate the speed of the ether. And I think that's as far. Remember, we always need to stay relevant to the question. Okay, question 19. Two straight copper wires are suspended so that the lower ends are dipped into a conducting salt. The length of each wire is 35 centimeters, and they're placed 1.5 centimeters apart. The ends do not touch the bottom of the beaker. The two wires are connected to a DC power supply. Current of 2 amperes flows in the battery from the battery. Calculate the magnitude from and direction of the initial force on each wire. So this current is going to be traveling in opposite directions, right? So meaning that they would repel each other. So that's the direction is going to be repulsive, and the magnitude. So that we have current, we have our two lengths, we have the distance apart, and we have the coefficient, so we can do that. Two solenoid coils, hollow cores are suspended in, okay, they do that, free to move in the pendulum. So straight away we should be thinking Lenz's law. In the first of, so this is just basically this one here. Figure 1 and Figure 2 are demonstrating the same thing, except for Figure 1. There's nothing that's connecting A and B. Alright, so in Figure 1, Lenz's law would like to apply, right? And it would to a small effect, but since that we don't have this copper wire, we can't. This circuit here is open, so it can't generate a magnetic field on its own. So this is not going to have any effect. Whereas this one here, Lenz's law, will create a back EMF. So at first it's going to try to repel the magnet, and once the magnet's in and we pull it back out, it's going to move with the magnet and become attractive. So this Figure 2 would start swinging. And it's 4 marks, so it's probably 2 marks for explaining the effect. 2 marks on each figure. Explain the relationship between the current in the primary coil and the current in the secondary coil in an ideal step-down transformer in relation to the conservation of energy. So remember, step-down is voltage is being stepped down, but due to the conservation of energy, the power must stay the same, and thus current actually goes up, which is a pretty cool concept. Explain why a transformer will work on an AC current but not on a DC. So transformers need a fluctuating lines of flux. AC AC electrical power supply provides this, whereas DC provides a constant flux. So explain 2 marks, mention both AC and DC. Describe the first time, okay, so question 22, alright, let's do this. Describe the first time investigation to demonstrate the effect on a generated electric current when the strength of a magnet is varied. Alright, so this is your aim, equipment, method. The most important part of these type of questions is the results, because when you write down results, even though if you're lying about it, it's proof that you've somewhat, or that you have done it. So you need to write results, and then you need to write or write a sentence about explaining the results. So the most important part with these questions is results. So main method, and then results, conclusion, and 5 marks. So we need to put a nice diagram. Okay, question 23. The following image shows a magnet hovering above a superconducting disk. Explain why the magnet is able to hover above the superconductor. 3 marks. Explain. Alright, let's start off with identify. So, say we knew nothing about this HSC Physics. Even if we knew nothing, straight away just identifying and just defining what is in the question. So, it would be a good idea to identify what a superconducting material is. A material that has no resistance. And then from there we can go into Lenz's law. Lenz's law is, and then fill it out. When we mix a superconductor and Lenz's law together, it results in a magnet being able to hover. You can probably word that better, but that's the general basis of how you want to explain questions. Okay, question 3, another 3 marks. Compare the model of the conduction of electricity in metals at room temperature. Alright, so compare. Straight away, draw a line through the middle of this page. Straight away, put conductors in one column and superconductors in another, and just write features, similar and different features about them all the way through. So superconductors, zero resistance, normal conductors have some resistance, just straight away, and it's compare the model. So definitely put a diagram on how electricity is transmitted. So in this case, we need to explain why superconductors have zero resistance. Alright. Question 24. Outline Thomson's experiment to measure the charge to mass ratio of an electron. So again, I think this is just a memory thing. He equated 2 of the motions. Well, I think he first used the electric field to deflect it, then he used the magnetic field to make sure that it travels in a straight line. But he used the deflection because he could actually measure the arc. Anyway, so then he equated those 2 equations, and then you can get charge to mass ratio, which is, fancy. It proved that, these are particles. These are electrons. Okay, question 25. A physics student was conducting an investigation on the photoelectric effect. Calculate the energy. So since it's 2 marks, I would write down just the equation. And then the next step would be to substitute. So E equals HF. We know the value of H. We know F, or we can just put V over lambda. That'll give us F. And then calculate the energy. When the laser light is shown onto a photocell, no current was detected. The student increased the intensity, but still no current was detected. Explain this observation. So this is basically wanting us to tell that intensity or current is not dependent on intensity, but the frequency of those cells. Why? Because frequency is dependent on energy, and those electrons need enough energy to get released, if that makes sense. So definitely write the equation. E kinetic energy is equal to HF minus the work done on the material, so i.e. the amount of energy the electron needs, and through the we should be able to determine, or to say, oh, it doesn't depend on the intensity, it depends on the frequency. Anyway, moving on. Describe Einstein's contribution to special relativity and to quantum theory, and how these contributions changed the direction scientific thinking of in the 20th century. 6 marks. Whoa. I would plan, like, just spend some time in planning. Alright, so let's dissect this question. Okay, it's a describe verb. Einstein's contributions to special relativity and quantum theory, and how so this is a verb modifier, so this is basically asking us to explain these contributions changed, so that's another big word, the direction of scientific thinking in the 20th century. This is one big juicy question. You can definitely split this up, special relativity, quantum theory. So we need to speak prior, we need to talk a little bit about before Einstein. So in terms of special relativity, we used to think that distance and time was fixed, and then before special relativity, it's actually the speed of light that's fixed, and time and distance can actually vary. So that's one way how he changed it. Quantum theory, so he has the ideas of photons, and he introduced the idea of light being able to be particle-wave duality. Yeah, that's pretty amazing. So prior to that, we thought light was just a wave, and then once these equations came in, now Einstein says, okay, yeah, it's also a particle. It's both. And if you go on to do quantum quarks, everything is actually a wave and particle. So that's cool. But yeah, definitely break up this question. And again, the big word here is change. We need to be explaining what he did in special relativity. So like maybe just write down his equations here and here. Yeah, and in these type of questions, we need to be putting as much maths into them as possible. But yeah, this is a nice question. I like that one. Alright, question 27. In a particle accelerator called a synchrotron, magnetic fields are used to control the motion of the electron so that it follows a circular path of fixed radius. Describe the changes in the magnetic field to accelerate an electron near the speed of light. Support your answer with appropriate mathematical relationships. So as it gets near the speed of light, the electron is going to get heavier, right? Because it's getting relativistic mass. So F equals ma. In order to keep it accelerating at its constant rate, we're going to need to increase the force that we put into the electron, meaning that our magnetic fields are going to need to get stronger. Ah, that was a lot. But this is a described question, but support your answer. That's definitely bringing it up to the next level of explain. It's 4 marks, so we need to probably describe what happens to the electron as it goes near the speed of light if its mass increases, and then we link the increase in mass with Newton's second law, F equals ma, and since we want a to be constant, we must increase F. We can bring in the equation QVB, and since Q doesn't change and V is always increasing, we also have to increase B so that it stays on the circular path of fixed radius. And there's going to be definitely marks for mathematical relationships. Alright, and that is it. So as you do these questions, you need to get good at answering 6 markers and 4 markers. Alright, thank you.